Hey everybody! This video is to introduce you to the last question on your exam. I like to keep data real, otherwise I don't really see the point. So I figured I'd share a story with you about me and my preferred method of transportation. Some of you know I'm a bike commuter, which means whenever it's possible and safe, I will take my bike to work and back, and to the grocery store, and to pick up my son from school and whatever. I've lived in Bend for about 14 years. I bike commuted well before that, before moving to Bend. But I discovered about 3 years ago that the ideal, at least in my opinion, year-round commuting bike is called a cyclocross bike. This is the bike that I actually have. A cyclocross bike is a mashup between a road bike, like if you ever see like a stage of the Tour de France or road bike racers, that's the kind of bike they ride, and a mountain bike, which is one of those bikes that you see the people out on the trails riding, big knobby tires. The cyclocross bike is a mishmash of those two bikes. It's got road bike sized wheels, but it's got a mountain bike type drivetrain. So it's designed, cyclocross races date back a few decades, but it's really designed to kind of bridge the gap between both worlds. It can ride on the road and it can ride on the trails fairly effectively. It doesn't do either one as perfectly as the other two styles, but it's a beautiful blend of the two, and that's kind of what makes it a nice commuting bike. So when I purchased the bike originally, I would take it to and from work. And I'll tell you a story. I decided to take it home one day on some local trails, and I noticed that I was having a really hard time stopping. I'll give you the exact location. Right above Sawyer Park, there's a trail that drops down from Aubrey Butte. When I came down through that trail system, I realized I got going so fast the brakes weren't stopping me, and I had to lay the bike down or risk falling off of a very, very large, steep hill. So I did some research, and what I discovered, I'm going to flip forward here a couple of, I discovered that the bike I had, and I knew this, had cantilever type brakes. Now, you don't have to know too much about bike terminology. Those are old school brakes. Those are the brakes that were the first lever actuated brakes that were available. They go back, again, decades. And I wanted to switch them to something a little more, what I assumed to be, based on my own personal history and experience riding mountain bikes, something a little more sturdy, which were V-brakes. Now, we'll talk more about V-brakes versus cantilevers. I did some research, as I often do. Here's some articles I found. Why doesn't anyone use V-brakes on my cross bike? Cyclocross V-brake question. And I learned some good information by reading these articles, and I learned that I had to put what are called mini V-brakes on. Again, you don't have to worry about that. So I got a pair of these mini V-brakes, and then I wanted to test to see if they actually did give me an advantage in stopping. Because the big problem was the cantilever brakes were not stopping me quickly enough, and I was getting worried with running through stop signs, getting hit by cars and things like that. So I set up an experiment, and here's the experiment that I set up. This is my house right here. Across the street from my house is a house with a very steep driveway right here. Here's a little better look of it right here. So what I did was I took my bike, balanced it at the top of this driveway right here, got into what's called a track stand. If you had me in 105, you saw me doing this back in 105, which basically means I got myself onto the bike, feet on the pedals, balanced, and then I let the brakes go. I didn't pedal, I simply let gravity pull me down this hill right here. Simply let gravity pull me down this hill. Then my front tire left the sidewalk right here. At that moment, I began carefully applying the brakes on the front and back simultaneously. And then I had a tape measure laid out across the street, starting at that point, I'll back up here, starting at the point where I left the sidewalk, and I ran it all the way across the road just in case I needed it. But I didn't. I stopped every time I stopped somewhere in the road. I had my son give me a hand. There's Max a few years ago, giving me a hand with the science experiment. I said, Max, buddy, I need you to make a mark where the hub of my wheel lines up with the tape measure. So you can see he did a pretty good job. I made sure to make note of the correct measurements in each of these. He did a really good job helping. He was totally into it. And I did this multiple times for both the original cantilever brakes And then I installed the V brakes and did it again for those. So I had two sets of data. I had the sets for the cantilever brakes, and then I had the sets for the V brakes. I did them on 2 days where the weather conditions were the same level of humidity, same level of warmth. The asphalt was roughly the same temperature, so there weren't any other confounding variables. I used the exact same tires on the bike each time. The only thing that was different was that I had the cantilever brakes on for the first test and the V brakes on for the second test. Here are the cantilever brakes. That's what they look like. So you can see what happens. That you pull the brake lever, this lever goes up, these pull up diagonally, and then these go up, and then these go in. It's like a Rube Goldberg mousetrap machine. Okay, so that's the way cantilever brakes work. These are called V brakes. Crazily enough, they're shaped like a U, but these are called U brakes. Don't worry why. It's stupid bicycle history. But the way these work is you pull the brake, it pulls this thing across, and then both of these head straight in. Now, what you can see by looking at the data is if you look from here to here, this is feet it took me to stop to a complete stop. Here you go. That's the data with my cantilever brakes. That's the data with my linear pull, or what are called V brakes. Okay? So what I want you all to do in your assessment is you are going to, first of all, make sure that even though these numbers look larger than these numbers, which they do, I want you to test it statistically, which means you're testing it scientifically, by running them through technology to actually say, yes, there is a statistically significant number of feet difference between the linear pull and the cantilevers. And I also want you to form the margin of error around that by constructing the confidence interval. Now, because you have two different groups, you got the before and you got the after, you're going to have to use a two-group independent confidence interval for two means. But if you look at the Excel spreadsheet, you'll be able to figure out what it is. So I'll give you some hints here. You're already, if you did the previous few problems for the exam, you're already in the correct spreadsheet. But since these are measurements and not counts, that's why you need to have a different calculation tool, right? You need to have a different calculation tool because you're not counting, you're measuring now. Okay? So look in the sheet and figure out what tool you're going to need. I'm going to give you a second hint right here. You also are going to need to take this raw data and distill it down into summary statistics. I would use one of the sheets from Math 243 to do that. If you didn't have me in Math 243, those are the green sheets in the Excel spreadsheet. Okay, those are the green sheets in the Excel spreadsheet. So you'll have to use some of those to take these numbers and crunch them into summary statistics to then feed into that spreadsheet. Okay? That'll get you started. Excuse me. That'll get you started. If you get stuck with this, give me a shout. But I think you're ready for the last question on the exam. Be well, friends.